Hey everybody, this is Dr. D. Hope you guys are doing well. The last thing I talked about, I think, was central location. So if you're watching the playlist, you should have heard about central location, and now we're going to move on. Where we are, we're talking about statistics. In particular, we're talking about descriptive statistics as opposed to inferential statistics where we make guesses. Descriptive statistics is how we describe our data. And we're not talking about visualizations right now. We're talking about numerical measures. One of those, the most important group of numerical measures, probably, is measures of location. And we talked about central location last, right? The central location measures we talked about were mean, median, and mode. But lots of times we don't just care about the middle, right? Like reducing a data set, all the complexity in the world into one point in the center, that's reductive. And that reduction is important. I mean, the purpose of these numerical measures are to reduce the complexity of data, right? Statistics is all about taking a very messy world and reducing its complexity to get meaning, right? To extract meaning. But sometimes that meaning is not just where's the middle. And so we have other measures here. In particular, let's say, we want to give an award to our best employee. Well, our employees, our sales reps might have some sort of, we might score them in some fashion. And here we might have our worst score. Up here we might have our best score. And yeah, maybe the middle matters, right? Maybe there's a median or the mean. But what we might want to do is provide some sort of incentivized reward to the top 10%, right? So these people, all the people who have scores in this range, are the top 10%. In order to do that, though, we need to know what score qualifies you for the top 10%, right? So that anybody who gets above that is there, and then everybody else is in the bottom 90%. Now, none of the tools that we've learned about can help us do that, right? What we need to do is find some way to split our data into two groups. We might care about this for other reasons too, right? Not just this example, but there are lots of examples. If we're in accounts payable and we want to look at our 20% most delinquent accounts, right? We might want to know, well, how much money is in just those, and is that a real concern? If that's where most of our missing money is, that's important. If they're relatively low accounts, then it might not be worth putting a lot of effort into collecting on them. We can charge them off or something. But in order to do that, we're going to need to think about how we can measure different parts of this entire distribution. So what we're going to do is we're going to provide this kind of measure by defining a new measurement that we'll call a percentile. In particular, we are going to talk about the Pth percentile, where P will be a number between 0 and 100. Right, so we'll talk about the 25th percentile, or the 47th percentile, or the 90th percentile. And the Pth percentile, so the P is going to be a number that tells you where the percent is. But this is going to be a value, like a value measured in the units of x, right, whatever our variable is. So it's a value that splits our data into two groups. And those two groups are going to have, that P is going to tell us how big each of those groups are, right? What we have then is we have P% of our observations have an X that is less than or equal to our percentile. So our percentile is going to be a number, and P% of our data is going to have a lower value than X. And 100 minus P% of our observations will have an X higher than that value, right? And so that's kind of what we have up here, right? 90% of our observations fall below this value, and 100 minus 90, which is 10, have an observation, 10% have an observation above this value. What that means is that this value right here, right, if this is x, whatever this value of x is, this is our 90th percentile. Up here. That's what it is. It's 90th percentile. And so that's what we're going to do. So Let's say, for example, we're filling bottles at a plant, and we take a sample of 120 bottles. Well, then 90% of those, we know that the 90th percentile is 12.2 ounces of filling volume. 90% of the bottles in our sample, like 108-ish, will have a filled volume less than or equal to 12.2 ounces, and 10% of the bottles, other 12, have a filling volume greater than or equal to it, right? So we're splitting our data into two groups. In order to figure out what the value is, though, so what we're trying to do, right, to find a percentile is to pick this value. We need to find what that value will be that splits it like we want, right? And so in order to do that, we're going to turn this into two questions. The first question is, how many of our observations have to fall below, have to have x's that fall below our percentile? And once we know that, our second step will be to choose a value to satisfy part 1. So, part 1, how many of our observations have to have x's that fall below our percentile? Well, kind of the silly answer, but the answer is, well, p% of them, right? Okay, so p%, right, because that's how we defined it, right? P% of our observations have an x that's less than or equal to our percentile. So what is p% of them? Well, that depends on how many we have, right? So let's say we're looking for the 90th percentile, like up here, right? Well, if we have 1,000 observations, then that means 900 of them have to fall below it. That's 90% of 1,000. Alternatively, if we have only 500 observations, then 450 have to fall below them, right? Because that's 90% of 500. And so the answer, another answer, is that this depends on P and N. And so we're going to define what's called the rank. It's windy outside. The rank of our percentile, call it R, is going to be the answer to part 1, right? It is going to be p% of this. We will write that as P divided by 100. Put this in parentheses if you want. You don't have to. Times N, where P is the number of our percentile, and N is our sample size, right? Okay, so now we need P and N. What do we want to use? Let's see, I have some data here that I just pasted in. Let me slide it down a little bit. We'll try to calculate rank here. Okay, so in this case, I have current temperatures. These were current temperatures in the West on August 22nd, 2012 or something like that. I don't know, it was a while ago. But I just looked at a map on weather.com and I just typed in some numbers. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers. So N equals 15. What percentile should we do? Let's do the 20th percentile? Let's do the 40th percentile? Yeah, let's do the 40th percentile. Okay. So what is the rank? How many numbers, if we want to find the 40th percentile, how many numbers have to fall below that? Well, R equals 40 over 100 times 15. Okay. What's that equal to? Well, that's equal to 4 times 15 divided by 10, which is 60 divided by 10, which is 6. And the way I did that, I just cancel this, and then 4 times 15 is 60 divided by 10, you get 6. So the rank of the 40th percentile is 6. So that says that if we want the 40th percentile, then 1, 2, 3, 4, 5, 6 of these numbers have to fall below it, right? What about, let's say we want to look at the 75th percentile. In that case, N equals 15 again. P equals 75. Okay. Now we have R equals 75 over 100 times 15. Well, now this is 3/4 times 15, right? times 15. I'm not sure how to make that in. There we go, times 15, which is 45. That should be a fourth. 45 divided by 4. Well, that equals 11.25. Okay, that says that 11.25 of our numbers have to fall below that, right? And so you can do this for any set of things. Let's say we had 320 observations, and we wanted to find the 50th percentile. Okay, in that case, R equals 50 over 100 times 320, which is 320 divided by 2 equals 160, right? So 100, the rank of that percentile would be 160. Okay, so that's step one, right? How do we, let's calculate the rank. How many observations have to fall below it? Okay, well, now to go from here to the actual percentile, there are a couple different options here. Let's look at it first this way. Let's say if R is not an integer. Let's say R is an integer first. That's probably easier. So let's say R is an integer, no decimals. What do we need to do? Well, what we can do then, as in this case, right, where R was 6, we want to make sure that 6 of them fall above it, right, and the rest fall below it in terms of value. The rest fall above it in terms of value. So what we usually do is we take the rth number, right? Call it, maybe we can call it x sub r, and the r plus 1th number, which is x sub r plus 1, and find their average, right? That'll be our percentile. Because that'll split this difference, right? We just want a number that falls between these two. In this case, the average of 55 and 55 is 55. And so the 40th percentile is 55. Right? Convenient enough. If we were looking at the 60th percentile, what would that be? That would be, does that one work easily? No, the 80th percentile maybe works nicely. I'm trying to think of another one that comes out even. Yeah, that's fine. So we have a whole number. Take rth and r plus 1th and divide by 2, and that's your percentile. What if we have an integer then? Well, if we have a decimal. If we have a decimal, it gets a little bit trickier, partly because we're dealing with relatively small data sets. If we were dealing with larger data sets, a lot of the different methods would come to equal the same thing. The way that we will handle this, the way that I like to handle this, just because it works fine, is to just take this value, take r, so if r is a decimal, you just round it up. Call r hat the next largest integer. Right, so 11.25, r hat equals 12. Then your percentile is the r hat number. So in this case, it would be the 12th number. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 58 degrees. 58 equals the 75th percentile. Okay. And that serves the function of setting 3/4 of them at least less than or equal to that, and 1/4 of them at least 1/4 of them as greater than or equal to them, right? Because you know that'll get us there, right? So now in this case, 12 out of the 15 are less than or equal to, that's 80%, and 4 out of the 15, that's more than a quarter, right? So that's how it works. With larger data sets, that is not, it works out a little bit more smoothly. Now, because the truth is, or the problem, the reason that that's kind of up in the air is because there are a lot of numbers that would satisfy that, or there are often a lot of numbers that would satisfy that value, because we need 11.25 of them to be lower, and you know, so what we can do is often to try to find many different numbers that will satisfy that. We just pick one. Excel actually has 3 different formulas for percentile. And if you go to Wikipedia, you can see a lot of different formulas as well. When n gets large, they all kind of converge to the same thing, and it does. You know, it's not such a big deal. But for small n, you got to be careful about which one, you know, whoever you're doing it for wants you to use. Okay, so that's how we calculate percentiles. And percentiles help us to describe sort of the fuller shape of the distribution. And so, we take our whole distribution and we can cut it into pieces and then talk about it. Now, some of these percentiles are really important. Before we talked about the center of this, right, the middle of our data, called the median. Well, the median has half the data that are lower than it and half the data that are greater than it. And since half is 50%, we call this the 50th percentile. If we want to describe just the general shape of the distribution, one thing we can do is to kind of cut the rest of this in half as well, right? So we can find it so that we have 1/4 of our observations below here, and then 1/4 of our observations above here, and this will be our 25th percentile. And because it has 1/4 below and 3/4 above, right, a half over here plus 1/4 over here, we call this the first quartile. It's a special percentile, it's a quartile, and sometimes we abbreviate it as Q1. Okay. In addition, to finish off the other side, we can split this in half. And so now we have n over 4 observations here and n over 4 observations here roughly. And this is our 75th percentile. This is Q3, our third quartile. Now, in addition to being called the median and the 50th percentile, this is also the second quartile, Q2. And then the minimum over here is the 0th quartile and the 0th percentile, right? 0% of them are less than or equal to it, and 100 minus 0% are greater than it. So sometimes we call this Q0. And then up here we have our max, which is Q4, right? Because 4 quarters are less than it and 0 quarters are greater than it, or 100, or it's the 100th percentile as well, right? Our maximum value. And so there you go. These are Q0, Q1, Q2, Q3, and Q4. These really fully describe our data. In fact, sometimes we call these, we take those numbers and we can call it a 5-number summary. If you really just want to chop your data into pieces to give an idea, the 5-number summary is Q0, Q1, Q2, Q3, Q4, and sometimes that's rewritten as min, Q1, median, Q3, and then max, right? Because that's what they are. And that tells you a lot about a data set, right? I mean, if you just have that, you can figure out if it's skew in one direction or the other, basically, or at least some measure of it, where the median is relative to the endpoints and the extreme values, and then how spread out your data is. We'll talk more about how spread out it is in a minute. Okay, so those are the major measures of non-central location: percentile and quartile. And percentile cuts it into 100 pieces, right? Quartile cuts it into 4. And some places you might see some other measurements like this. Quintile, for example, is not uncommon, and this cuts it into 5 pieces. It's the 0th percentile, 20th percentile, 40th percentile, 60th percentile. So when you see like top 20% of income earners, they're talking about that top quintile. And then sometimes if we want to cut that a little bit more fine, you might have decile, which is 10 pieces. And those are the terms that you'll hear people use sometimes. But in all cases, if we want to calculate the first quartile, usually what we do is just calculate the 25th percentile the way that I showed you above. I believe Excel has formulas for all of these. Excel has a quartile function and a percentile function. And so you can use Excel there. There you go. Cool. So those are measures of non-central location. That's all the location we really are going to need between the central location and the non-central location. The next thing we'll do is start talking about how to describe the spread outness of our data, our levels of dispersion. So stay posted, and I'll be back soon. Thanks. It's Dr. D.